This excellent blog post, The Illustrated Transformer, helps us visualize it. Let's begin by looking at the model as a single black box. For machine translation, it takes a sentence in one language and outputs another.
Okay, so the familiar sequence-to-sequence setup, but what makes this black box different on the inside? How does it avoid the sequential bottleneck?
Peering inside, we find an encoding component, a decoding component, and connections between them. This encoder-decoder structure is common in sequence-to-sequence models, but the transformer implements it uniquely.
So it's still an encoder-decoder. Is it like the autoencoder idea we covered in ASH TCM 192203, where the encoder compresses and the decoder reconstructs, but for translation?
It's similar in principle, but the implementation is very different. Here, the encoding component is a stack of encoders, typically 6. Each encoder refines the input's representation, passing it to the next.
A stack? So each encoder builds on the output of the previous one. Does that introduce some kind of sequential dependency again, even if it's not word by word?
Good question. Within each individual encoder, the encoder's inputs first flow through a self-attention layer. This is where the magic happens for parallelism. It's not sequential within the attention mechanism itself.
Self-attention. So it's not looking at other sentences, but at itself? The words in the same sentence are paying attention to each other?
Exactly. Think of the sentence, "The animal didn't cross the street because it was too tired." To understand it, the model needs context. When the model is processing the word it, self-attention allows it to associate it with animal.
That's brilliant. So instead of a human defining rules for pronoun resolution, the model learns these connections inherently. It's like a focused internal conversation.
Precisely. This article calls it the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing. It's a way to contextualize each word based on all other words in the input.
So it's not just a pass-through. Each word's representation is enriched by information from every other word. That's a powerful idea for understanding nuance.
And the key to parallelism is how this works. The feed-forward layer does not have those dependencies, however, and thus the various parts can be executed in parallel. This is where it breaks from the step-by-step RNN processing.
So the self-attention part connects everything, but the feed-forward part processes each word independently after that connection is made. That makes it efficient.
Yes, it creates a rich, contextualized representation for every word, all at once. But how does this self-attention actually calculate which words are relevant and by how much?
Right. The intuition makes sense, but I need to see the mechanism. What's the mathematical trick that allows a word to pay attention to others?
Let's dive into the core of self-attention. For every word's input vector, the first step is to create 3 vectors from each of the encoder's input vectors. These are the query, the key, and the value vectors.
Query, key, value. This sounds like a database lookup or a dictionary. Is that a useful analogy, or does it break down quickly?
It's a very useful analogy to build intuition. What are the query, key, and value vectors? Think of the query as what you're looking for. The key is what you're matching against, and the value as the content you retrieve.
Okay, so if I'm a word, my query asks, what other words are relevant to me? And other words use their keys to say, here's how relevant I am.
Exactly. The next step is scoring. The score is calculated by taking the dot product of the query vector with the key vector of every other word. A higher dot product means more similarity or relevance.
So my query vector compares itself to all the key vectors. If my query for it strongly matches animal's key,
then animal is highly relevant.
After scaling, we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. These normalized scores become the attention weights.
So it's like a probability distribution. If a word is highly relevant, it gets a high score, and a low score for irrelevant words. This makes sense for blending.
That's exactly right. The final step is to multiply each word's value vector by its corresponding softmax score. The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words.
Okay, so its query gives high weight to animal's value, and then all these weighted values are summed up. The output for it now contains a strong component of animal.
Precisely. The result is a new context-aware vector for it. This process happens simultaneously for every word in the sentence. That's the power of sum up the weighted value vectors. This produces the output of the self-attention layer at this position.
So every word effectively runs its own query against all keys, then uses those weights to create a blended value from all other words. That's the parallel contextualization.
Crucially, after self-attention, the exact same feed-forward network is independently applied to each position. This means those learned contextualized representations can then be processed in parallel, without any further cross-word dependency.
I see. So the self-attention handles the dependencies, and then the feed-forward network acts like a local expert for each word's newly informed representation. No bottlenecks.
Exactly. This elegant mechanism allows the transformer to understand global context and process sequences efficiently. Now, imagine taking this idea, born for language, and applying it to something completely different. Images.
Images? But images aren't sequences of words. How could a model designed for language possibly work for pixels? That feels like trying to fit a square peg in a round hole. Okay, Arjun, I'm still trying to wrap my head around this. How can a transformer designed for natural language be used for image recognition? Do we just flatten the image into a long pixel sequence?
That's a very natural first thought, Maya. This paper, An Image is Worth 16 by 16 Words, tackles exactly that. It asks if we can extend the transformer beyond its NLP origins. The authors state, while the transformer architecture has become the de facto standard for natural language processing tasks, its applications to computer vision remain limited. They saw an opportunity to test the generality of the idea.
So they're not just trying to squeeze it in, they're making a strong claim about the transformer's fundamental power as a sequence processor.
Precisely. Their core finding is that a pure transformer applied directly to sequences of image patches can perform very well on image classification tasks. No convolutions needed.
Image patches as words? So instead of individual pixels, they break the image into small squares, and each square is treated like a token in a sentence.
Exactly. That's where the title, An Image is Worth 16 by 16 Words, comes from. Each 16 by 16 pixel patch is essentially an input word or token for the transformer.
Okay, so the image is flattened into a sequence of these patches, and then the self-attention mechanism we just learned about applies to how these patches relate to each other.
That's it. The Vision Transformer, or VIT, takes this sequence of flattened patches and processes them, and it attains excellent results compared to state-of-the-art convolutional networks on various benchmarks.
Wow! So a model that doesn't explicitly understand 2D spatial relationships, but only understands token relationships, can beat models built on convolution?
It implies that the spatial understanding is implicitly learned through self-attention, just as linguistic context is learned. And crucially, it requires substantially fewer computational resources to train than complex CNNs.
This confirms the initial promise of the Transformer paper about efficiency. It's not just about performance, but also the practicality of getting that performance.
One nuance, VIT performs best when pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks. It thrives on vast data for initial learning.
So, while general, it still needs that broad exposure to learn the fundamental relationships between image patches, similar to how large language models need huge text corpora.
Absolutely. The transformer has proven to be a truly foundational idea. It taught us that attention isn't just a component, but a powerful mechanism for building highly parallel, general-purpose sequence processing models.
From sentences to images, the Transformer showed us that the right way to think about many problems is as sequences, where every part can dynamically attend to every other part. I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.